Okay. Hello everyone. Again, I'm here today. Uh, this is our third class. Okay, second class. Yeah, second class. It's our second lecture. So in today's session, what I'm going to discuss is the various different kind of the operating system. In short, basically, I'll be discussing about the evolution of the operating system, how it has been evolved from the ancient to current days. Okay, and then after that, after a short description of evolution of an operating system, we will discuss a brief about the CPU scheduling because initially, in order to begin the session, okay, about the operating system, CPU scheduling is very important, and we all should know from the beginning itself, so that we can think from that perspective. Okay? So, in case of the evolution, what we are trying to understand is that the difference between the single user and the multi-user. A single user, you can consider the example you have heard about the operating system like MS-DOS. Okay, so DOS, disk operating system. Disk operating system is an example or the typical example for single user system or batch system, we can say. Okay. And then another category based on the user is the based on the type number of users, multi-user system. Okay. In case of multi-user system, the main idea is how can you execute multiple program at the same time. I repeat, in case of multi-user system, how can we execute more than one program at the same time? Whereas in case of single-user system, it is always possible to execute only one instruction at a same time. Execute means execution will be done by the CPU. So that is the aspect, and in there you can see in the diagram the logical architecture of the single-user single user system. You can see in the diagram that there is a user program. So this user program can be a single command or maybe a group of command, but a CPU will execute only one command at a time. So that is the example of single user system. And in case of a multi-programmed operating system, a multi-programmed multi-user system, here in the memory, okay, computer memory, there are residing more than one program of different category. And in case of the third one, that is time sharing system or multitasking system, here you can see there are many users and different terminals. You can assume you can have an assumption kind of thing like these terminals are the different CPU. Yeah, CPU given to different programs. Okay, so we'll discuss these things in detail now. Okay, so first of all, single user system. Single user system is also known as batch system. Now, why batch system? Okay, because in olden days or during those times, okay, very old times, there were a limited number of resources, and the resources has to be utilized efficiently. Now, what are resources? Resources could be printer, etc. Okay, so printer could be has to be used efficiently. Okay, now how? So in those times, the programs whose resource needs were same. Okay, like a resource may be a memory, a printer, etc. So the programs whose needs were same or whose demand of the resources were same were grouped together. Okay, were grouped together in a one batch. We grouped together in a one batch, and those batch or that grouped batch is given to the executor or the operator. Then that operator, what he used to do is that he used to execute the program batch by batch. Okay, so in a batch, based on the need of the resource, the programs were grouped together called a batch and were executed at once. So how they used to execute with the help of the various different cards. Okay, they try to use the punch cards where they store the programs and load the program every batch by batch into the system, and then press the execution button. Okay, and then they used to get the output, and those output has to be again stored in the another batch. Okay, another card. Okay, so those were the very tedious tasks that they used to perform to execute their users program. So the here the thing out here is that uh, the programs, okay, or the group of programs whose resource needs were same were grouped together and were called to be batch, and operator used to execute the program batch by batch. Okay, so that is the basic idea. So suppose in the left hand side you can see in the green diagram. Okay, so there is a memory. This memory is a typical representation of RAM. Okay, so because we already have seen in our discussed in our earlier session that whenever we want to execute any program, it has to be loaded into the computer memory. So this is just the logical representation. So entire RAM is divided into sections. One, the small portion of the RAM is always reserving the operating system, and the remaining is the user program. Okay, so now suppose the size of the memory of the user program space. The size of the memory of the user program space is 100 uh, and this batch of a program is suppose 50. Okay, 50 kb, and another batch is suppose 30 kb. So there are two batch that has been made, batch 1 b1 and b2 as batch. Okay, so although 100 kb amount of memory is there for both, which can accommodate both, but still in case of batch system only one batch can be loaded at a time. Only one batch can be loaded at a time in the user space for executing the user program. So this is the basic working principle of batch operating system, where a single batch of job is loaded into the computer memory and were executed with the help of the operators. Okay. Now, this way of executing the program is very inefficient. Okay, this way of program is very inefficient because, say for example, B1, that is batch 1, is loaded in the user space for executing. Now, during the execution of the command that is there in the batch program, suppose one command is there which requires user input. Okay, so say for example, scanf in C. So it requires user input. Now, during the user input, suppose user have not given the input, then CPU will keep on sitting idle, waiting for the user when he or she will enter the input and he has to process the some computation. Okay, so in that case, CPU is ideal. So we don't want that. We want always the CPU to maximally utilize the resource. Okay, CPU as a resource. So we want CPU to be busy all the time, always doing some task. So that is the main objective to make for working principle. Okay, now in this kind of batch OS, one thing that you need to note down out is that job scheduler. Okay, what is a job scheduler? Because the it is the responsible job scheduler is a program. Job scheduler is the program that is there with operating system. Okay, so the job of the main task of the job scheduler is to bring or is to select the job from the secondary storage device. Okay, based on the need or based on the demand. Out of so many batch, it will select one batch at a time and put it into the RAM. Okay, that is the user program space. So that is the job of the job scheduler, and job scheduler is the program that is there with the operating system. So it is the job scheduler program who is responsible for picking up the one batch from the secondary storage device and put it in the main memory. So these are the things that you need to note down in the single user system. And one thing that you need to focus out here is that what happens when the running program is like demanding for IO operations, and IO operations not being completed. So at that point of time, CPU is sitting idle, and we don't want that. Okay, that is very important, and that is the drawback of single user system or the batch system. So with this drawback of system, okay, people were thinking like, oh, okay, fine, how can I maximize the utilization of CPU? So they were thinking and they come to the conclusion like multi-program system. So in case of multi-program system, what was happening is that entire memory that you can see in the batch system, that entire memory of the user space were divided into different partitions. Okay, so the size of the partition may be equal or maybe unequal. That is not of concern right at this moment of time. So somehow the other day, the user space is divided into different memory segment called partition, and each partition has the ability to store different jobs or the different batch of jobs. Okay? So say for example, we have considered in this diagram there are n number of jobs I have stored in different partition. So In case of multi-program system or multi-programmed OS, in case of multi-programmed OS, the user space or the memory is divided into different partitions, and inside which the jobs will be selected, okay, and will be initialized in the computer memory for execution. So job will be selected from the secondary storage device, and it will be put into or kept into or initialized into different partitions. So say for example, job 1 has been selected from secondary storage device and has been initialized in the first partition, whose memory location is ranging from 100 to 150. And similarly, job 2 has been selected from the secondary device into the main memory or RAM, starting from memory partition starting from 150 to 200. Like that way, different jobs were uh, initialized in different partition for execution. Now, in order to overcome, let us discuss, how can we overcome the problem of batch OS. Suppose the CPU is executing job 1. Suppose CPU is executing job 1, and somewhere in between 120 line, okay, or at 120 memory location, there is some IO operation that it requires. Some maybe input operation from the user input it requires job 1. So at that point of time, CPU will not wait for I operation to get complete. Okay, CPU will directly jump over to job 2. Okay, assuming that the I operation will go in the background of the job 1. Okay. So like that way. CPU will switch from one job to another job, highlighting that how it tries to execute multiple job at the same time in the time multiplexed fashion. So how multiple jobs is being executed in the multi-program OS. So say for example, at time t equals to T1, job J1 has initiated its IO operation. Okay, job J1 has initiated its IO operation, input output operation. Okay, and at the same time, job 2 has started some computation operation by the CPU. So job 1 is performing what? Job 1 is performing IO operation, and job 2 is performing computation operation. So IO operation is performed by the IO devices, and computation is performed by the CPU. So at same time, in a time multiplex fashion, one resource CPU is executing some task. At the same time, IO operation, some input output device is performing another task at the same time. So this is how we can say, we can define that. Okay, how multi-programmed OS is performing the multitasking at the same time. So this is all about the story of how a multi-program OS works. Okay, now here two important terms you need to remember: CPU scheduler and job scheduler. Okay, job scheduler you have already encountered. The job scheduler is the program which is there with the operating system, which is there inside the operating system, which has the ability to select one job or multiple job at a time from the job pool. Okay, which is job pool means job pool is the pool of job which is there in the secondary storage device. So from the secondary storage device, it select some jobs out of 100. Say for example, each job select 5 job at a time and initialize in the 5 partition of the OS. So that is the job. That is the main task of the job scheduler in multi-programmed OS. Say for example, there are three partition. Okay, and out of 100 job in the job pool, that is in the secondary storage device. Job pool means job pool is the area where you keep all the jobs. Okay, in the secondary storage device. So job scheduler will select out of 100 job from the job pool. It will select, say for example, 3 job at a time and put it or initialize into the partition. Now whichever jobs gets completed first, completely executes completed first, the job scheduler will shift the corresponding job from the main memory to the secondary. So that is the task of the job scheduler, bringing job from the secondary storage device to main memory and sending the job from main memory to the secondary storage device. That is the job of the job scheduler. Okay, so main task we will consider only how to bring which job it has to bring from the secondary storage device to the main memory is the job of the job scheduler, is the task of the job scheduler. So that's why it's called out here job scheduler selects job to enter the system. Okay, so this is a task of the job scheduler in multi-programmed OS. In case of the batch OS, job scheduler was selecting only one job or only one batch at a time from the secondary system. Whereas in case of multi-programmed OS, initially it will select based on the number of partitions, and based on the later on it will select based on the number of free space or free partition that is available for executing the user program. Okay. So that is the task of the job scheduler. Now next we need to understand what is CPU scheduler. Okay. Now CPU scheduler is responsible, or CPU scheduler is also a program that is inside the operating system whose task is to assign CPU. Okay. Like the way that I've given the example. Suppose job J1 was going to execute IO operation at memory location 120. So when operating system will about to know that okay, at job J1 is going to execute at line number 120 of job J1 is going to perform some IO operation. So at that time, CPU scheduler, what it will do? CPU scheduler will at that time, at whenever it reaches 120 location, CPU scheduler will assign CPU to job 2. Okay, so like that way it will try to perform the task. So what is the job of the CPU scheduler? Is to select the job. Okay, is to select the job which CPU has to execute it. So CPU scheduler schedules the CPU, okay, or the processor. Okay, so that is the job of the main task of the job scheduler and CPU scheduler. So now here in the time multiplex fashion, we are trying to execute the task. So always whenever we have to, whenever we are studying any kind of OS, we always has to think from the point that how efficiently we can execute the user task. So that is the main task of the operating system, as discussed in our earlier session, that what is the main aspect of design. Okay, so we'll move ahead. Mm, Now problems. Okay, so recall the problem of the batch was only one task you can execute at a time. So memory is not utilized efficiently. So now in order to utilize the memory efficiently, hello, am I audible, students?
Yes, sir.
Yes, sir.
Okay. So I was talking about the problem of batch OS. Okay, in case of batch OS, um, in one memory location, only one batch of job was able to like initialize. Suppose there the amount of memory in batch OS is 100 KB, and you have got only 50 KB. Remaining 50 KB is being wasted. Okay, that we don't want in multi-programmed OS. Now, in case of multi-programmed OS, okay, there are multiple partition of the memory in which multiple jobs are there. Okay, so in this different multiple partition, you will see the screen after some time. Okay, uh, uh, in this multiple partition, there are different jobs that is initialized. Say for example, job J1 initialized in partition 1, job J2 is initialized in partition 2, and job J3 is initialized in partition 3. Okay, so this is the scenario. Now, uh, um, hold on, okay, my computer is getting this started. Fine. Okay, okay, so here uh, you are trying to store 3 jobs at a time in a computer memory. Earlier, you were not able to do so in case of batch OS. But in case of multi-programmed OS, you were able to initialize or use computer memory efficiently by initializing different batch of jobs in different partition. Okay, so for example, there are 3 partitions in this example, so 3 jobs were initialized. Okay, so this is how it tries to efficiently utilize the memory. Okay. Have you understood, all of you? If you have any questions, please raise it. I'll wait for some seconds. Okay. Students are please feel free to ask the questions. Okay, we'll go slowly. Any questions?
No, sir.
Bolo, please. Yeah, please go ahead with the question. No questions? Somebody please respond. If there is any questions, please let me know.
No, sir. No questions.
No question.
Okay, somebody. Sorry, no questions. Okay, you'll get the screen after some time. Okay, so till now what we have discussed was the batch OS and the multi-programmed OS. Now, in case of multi-programmed OS, there is one problem. Can you anybody define the problem? You have already seen this slide. Can you define the problem? What could be the problem?
Fragmentation.
What do you mean by segmentation? What do you mean by segmentation?
Fragmentation, sir, not segmentation.
Okay, fragmentation. Okay, what do you mean by fragmentation?
Creation of whole.
Yeah. Can you elaborate it? How a whole is created? Hussein? I will ask the question, okay? By logging in and sleeping will not work. Ashish Tiwari?
Yes, sir.
Yeah, can you explain me how wholes are generated in case of multi-programmed OS?
When CPU switches from one job to another job.
So how wholes is created then?
Mm,
Hmm? Anybody volunteer? Hussein or Kritika? Hussein or Kritika, please. Correct. They are not listening me. Coming live, there are different things. Na? Coming, you have. I'm coming live means you can clear your doubts, etc. But otherwise, I could have recorded and give it to you. You need to take advantage of interaction. Hussein?
Sir, not sure, sir.
Okay, fine. So I'll take help of the example only. Okay, so in case of the multi-programmed OS, you have seen there were different partition, right? You have seen there were different partition. In different partition, different programs were there. Just hold on. Hello, am I audible now?
Yes, sir.
Yes, sir.
Okay,
Yes.
where were we? Where were we?
Sir, holes.
Yeah, holes. Okay. Okay, I hope I am audible now, for all of you. Okay. So, did you all of you understood the definition of CPU scheduler and job scheduler? Any of you, please respond. Okay. Am I audible, all of you?
Yes, sir, you're very much audible.
Please
Yes,
respond.
sir.
Okay. You all are given to flexibility to talk in between and intersect interrupt me in between. Okay, if there is any problem. So, what was the last statement that you have heard about me just now? What I was talking about?
Sir, on fragmentation, the problem of whole.
Okay. So the problem of have you understood the example? Example means how holes are created.
Sir, can you repeat that once? How holes are
Okay.
created?
Fine. Thank you. Yeah, okay. So suppose there are three partitions of the computer memory: 100 to 150, and 150 to 200, and 200 to 250. There are three partitions where you can insert the job. Okay. So the job scheduler will select out of 100 job from the secondary storage device. It will select 3 job. Okay, and initialize over here. It will initialize in first partition job J1, job 2 is initialized in second partition, job 3 is initialized in third partition. Now, after initialization, it is think you can analyze like this way. Suppose the size of the partition is 50, okay, and the size of the job J1 is 40. Okay, 50 KB is the size of the partition, and 40 KB is the size of the um, job. Okay, so when job scheduler tries to allocate the job one in this partition, it will create free memory space of, it will not occupy entire 50 KB of memory, it will occupy only 40 KB, so creating 10 KB hole. Okay, similarly it applies to job J2 and J3. Now this is the way with which holes are created. Okay, and this kind of problem is known as a fragmentation problem. Now, why fragmentation problem is the problem? Okay, because suppose there is a job J4 in the pool, and the size of the job J4 is, suppose it's 20 KB, and here the scenario in the memory is there are 10 KB each free space in each of the partition. Okay, 10 KB free space in each of the partition in scattered fashion. So total makes up 30 KB free space, but in scattered fashion. So there is a job J4 whose memory requirement is 20 KB. So 20 KB can be fitted into the 30 KB. Okay. Since those free memory space are in scattered fashion, you cannot assign job J4 into the computer memory, just because there is not enough free amount of memory space that is in continuous fashion. Okay, in a single memory block. So that kind of problem is known as a fragmentation problem. So the solution to the fragmentation problem is paging and defragmentation. Okay, in case of defragmentation, what is happening? You are reallocating each and every memory location, again reassigning the memory location, so that a continuous free space memory is created or can be created. So this is known as a defragmentation. So if you see the system tools inside system tools of your all programs category in your system, there you will find a defragmentation. Okay, so you can explore on it on your own. Okay, so that memory is utilized efficiently. That is one solution to the problem of holes, okay, or the fragmentation problem. Another solution to the fragmentation problem is paging. In case of paging, what is happening out here is that you divide the memory and you divide the program that you want to initialize into memory in equal portion. Okay, so if you see the definition of the paging is a memory management technique that will divide the program into equal portion called pages, and you divide the memory, computer memory in equal portion called blocks. Okay, so the program is divided in equal portion called pages, and the computer memory is divided into equal portion called blocks. Okay, the size of the block and the size of the page are equal, and then you load the page into the, you load each and every page into the computer memory for execution or for initiating execution. So there are two different kinds of paging. One is simple paging and the one is demand paging. In case of simple paging, in order to begin the execution of the program, all the pages has to be there into the blocks before initiating the execution of the program. In case of demand paging, only those pages which are essentially required for the initiation of execution, only those pages will be loaded into the computer memory in case of demand paging. Okay, let us take the example. Suppose there is a program, suppose there is a job J4, okay, and the job J4, the size is 10 KB, okay, and you have divided that 10 KB program into each page of size 1 KB each. So there will be 10 pages, okay, so 10 KB program is divided into equal portion of 1 KB each. So that's how you create 10 pages, okay, so 10 page is created. Now memory is divided into equal portion of 1 KB each. Okay, so 10 blocks is created. So there are 10 pages and 10 blocks for execution. Now in case of simple paging, all 10 pages has to be loaded into the blocks and then initiate the execution. Okay, whereas in case of demand paging, out of 10 pages, suppose only 5 pages is required to begin the execution. So in that case, in demand paging, only 5 pages will be loaded. So this is how your paging works, and paging is a memory management technique. There are two types: simple paging and demand paging. Okay. I hope I have made it clear. Somebody please respond if there is any doubt. Can we move ahead?
Sir,
Yes.
hello. Sir, can you explain paging once again, sir? Like I didn't quite understood. Demand,
What you have not understood?
Sir, demand paging, sir.
Okay, in case of demand paging, suppose there are 10 pages and there are, okay, 5 blocks. There are 10 pages and there are 5 blocks. Okay. Now, in order to begin the execution of the program, all 10 pages is not always necessary in modular program, any programming, right? So all the codes are not executed at the same time. Okay, so whichever page is necessary. Say for example, you have written the program, some program. Okay, you have written some program P, and it has got 10 subroutines. It has got 10 subroutines. So to begin the execution, it is not necessary that all 10 subroutines has to be initiated or loaded. So out of this 10 subroutines, say for example, to initiate the execution, it may be necessarily 2 or 3 subroutines has to be there into the main computer memory. Say for one of the routine could be a main program to begin the execution. Okay, so out of so many subroutine or out of so many pages corresponding to one particular program, only few pages are necessary to initiate the execution. So those pages will only be loaded in case of demand paging. And later on during the execution or after completing the execution of loaded page, it may require, suppose page 1, page 3 and page 5 has been already loaded, and during the execution of page 5, now it is demanding page 7. So again, it is demanding page 7. So operating system will bring the page 7 from secondary storage device into the main memory. So this is how demand paging works. Have I made it clear, all of you?
Yes, sir.
Okay. So we'll move ahead. Time sharing system. In case of time, the time sharing system is also known as a multitasking system. Okay. In time sharing system, or the time sharing system is the logical extension of the multi-program OS. It looks something similar to this diagram of multi-program OS, but actually the thing is, CPU time. Suppose CPU time. Suppose there is one CPU and CPU time will be sliced. Okay, it looks like CPU is giving time to each and every one. Okay. So CPU will switch so fast with different process that user will not notice that CPU is executing which program. Okay, so this is the object. This is how multitasking was. In case of multitasking, the CPU time is sliced okay, called a time slice, and each of the time slice is given to different process for executing the user program. In case of multitasking, the user can interact with the program in real time. Okay, and you won't even notice that CPU is with you or with you not. Okay, the main advantage of time sharing system is the resource utilization is very high. So if you compare the multitasking and the batch OS, in case of batch OS, the resource utilization was very high, but CPU the throughput, or the what do you call it, execution of different program was very low. Whereas in case of multitasking system, you can execute many tasks at the same time, but resource utilization is very low. Okay, so up till here, is there any doubt? So time sharing system. So high CPU utilization is the advantage of time sharing system, a multitasking system. Is there any doubt, please? Can I move ahead?
No, sir. Yes, sir.
Okay. So now we'll talk a little bit about the CPU scheduling, or the process scheduling, which you have already done in our last class. Okay. So I'll just repeat. It will be a revision for those that have not attended. So first, what we are trying to do out here is that we are trying to schedule the process. CPU scheduling. CPU scheduling is equivalent. You are basically trying to understand CPU scheduler. So what is the job of the CPU scheduler? The job of the scheduler is to assign CPU to job. Or in other words, you are trying to write down the program, or you are trying to understand the concept, with the help of which you are trying to understand that how to assign CPU to different process. Okay, so that is the main task. Okay, so suppose there is a job J1 with 15 units of CPU time it requires to execute it. So J2 requires 8 units of CPU time, J3 10 and J4 3. Okay. Now the order with which this job has been arrived to the CPU or they will come to the memory is J1 followed by J2 followed by J3 and J4. So the job have been arrived in the computer memory in this order. Okay. At the same time, I repeat, at the same time these job has been arrived. Okay, say for example, time is 0, time t equals to 0, this job has been arrived. So when it arrived, it immediately the program immediately assigned job J1 because job J1 have arrived at the system first. So CPU is given to J1 immediately for 15 units of CPU time. So immediately after 15 units, job J2 will get a chance of CPU for executing its code. Okay, so job J2 will get a chance at time t equals to 15 and use 8 units of CPU time to completely execute, and similarly followed by J3 and J4. Okay, so out here this is the orientation of the job with the help of which CPU will execute J1 followed by J2 followed by J3 and followed by J4. Okay, so now we have seen this. Okay, job J1 has not waited for CPU at any moment, for any moment of time. Immediately have received at the memory, job J1 was able to get the CPU and was able to execute it. Now after executing 15 units of job J1, okay, J2 has waited for J1 to complete. Since the burst time or the CPU user's time of J1 is 15 units, so J2 has to wait for 15 units. Similarly, J3 has to wait for burst time of J1 and J2, that is 15 plus 8, that is 23. Okay, so J3, in order to begin the execution of J3 have waited for J1 and J2 to complete its execution, because the chance J3 will get chance to execute its code, okay, with the help of the CPU only after completion of J1 and J2. That's why J3 have waited for 23 units of time, and similarly 33 units of J4, 33 units of time J4 have waited for its turn. Okay. If we talk about the average waiting time, so 0 plus 15 plus 23 plus 33 equals to 71 divided by 4. 17.5 is the average waiting time of all the process or all the jobs. Okay, so job and the process word is interchangeable. Okay, sometimes I'll say process, sometimes I'll say job. Okay, so similarly in this strategy, what is the strategy that operating system has used in this way of scheduling the process? They have used first come first serve. Since job J1 was arriving to the system first, okay, so you're giving the CPU first to J1 and followed by J2 and J3 and J4. Okay, now another strategy. Another strategy we have discussed in our earlier session is shortest job first. So out of these 4 jobs, whichever job is trying to use CPU time, very minimal CPU time, that job is given the first chance to execute. So in this 15, 8, 10, and 3, out of this set of jobs, J4 requires or uses minimum CPU time. So J4 will be given first chance. Okay, so J4 will be given first chance, followed by J2 and followed by J3 and followed by J1. So if you talk about this, so the average waiting time is shown out here. Okay. So 8.75. So if you compare these two strategy, okay, shortest job first and first come first serve, you can see average waiting time of shortest job for this less. So if you can compare these two algorithms, okay, so we can say that job SJF, shortest job first, is giving me the good average waiting time, or in other words, if I use shortest job first strategy while designing the CPU scheduler program, then if I opt this shortest job first technique strategy, it is going to give me the better result. In other words, it will not allow different job to wait for a quite long amount of time. So as a designer of the operating system, we always need to think that in whichever possible faster way we can execute it fast, that will be good. Okay, so that is the main objective of this two comparison. So now, in addition to these two which we have already discussed, the third one which I am going to take time is the priority scheduling algorithm. Okay, priority scheduling algorithm, in addition to the burst time is the amount of time that the different job requires for executing it. Okay, or it's burst time is the amount of time that CPU that job will be using the CPU. Okay, so here job J1 burst time is 15, means 15 units of CPU time will be used by the job J1 to completely execute. So in case of priority scheduling algorithm, in addition to burst time or execution time, priority will also be given. Okay, priority will also be given. So now the value, the numerical value priority can be considered in any way. For a time being, we will be considering that the low numerical value of the priority value considered to be highest priority, which means that 1 is considered to be highest priority, 2 is considered to be second highest priority, and then so on. Suppose this is the scenario: job J1, J2, J3, and J4 with burst time 15, 8, 10, and 3 are with the system or in the computer memory at the same time, and with the priority 4, 2, 3, and 1. Okay, so looking at this snapshot of the system, we can easily say that job 4 is having the highest priority because the priority is given 1. Okay, because the priority is given 1, so that's why job 4 is given the first preference to execute it. Okay, so CPU will be allocated based on the program, based on this strategy, priority scheduling algorithm. CPU will be allocated to job J4 because priority is 1. So job J4 will be executed for 3 units of CPU time. So till then, job J1, J2, and J3 will wait. Okay, now followed by J2. In case of J2, J2 will start at time unit 4. Okay, it will execute for 8 units of time. Till then, job J1 and J3 will wait. Okay, so since the priority of J3 is 3, okay, so third chance, so J3 will execute, and you can see the priority of J4 is 4, which is the lowest among the all. So job 4 will get the last chance to execute it. Okay, so this is the Gantt chart how CPU will execute in which order. If you consider the waiting time, the way with which I have told you how to calculate the waiting time, I already told you. You can job 4, the waiting time, job 4, the waiting time is 0. Job 2, the waiting time is the first time of job J4, which is equals to 3. So 3 units of time J2 will wait, and J3 will wait for completion of J2 and J4. So J2 burst time is 8 and J4 burst time is 3. So 8 plus 3, okay, 11. It should be 11. So 11. So job J4 will wait for J1. Sorry, job J. Yeah, it should be something wrong out here. I'll just correct it. It's job J1. Yeah, you can see job J1 has waited for J2, J4 and J3 to complete, which is the summation of their burst time 3 plus 8 plus 10, that is equals to 21. So average waiting time is 8.75. So at this moment of time, you have three algorithm or three strategy: first come first serve, shortage of first, and priority scheduling algorithm. These are the basic CPU scheduling algorithm. Okay, so job first come first serve, the average waiting time was 17, approx 17.5. Shortage job first, the average waiting time was 8.75, and priority scheduling algorithm, the average waiting time is 8.75. I doubt. Okay, just let us calculate 0 plus 3 plus 11 plus 21 and divide by 4. 8.7, yeah, 8.75. So if you compare priority and first come first serve, priority performance is good, and if you compare priority and the SJF, both are same. Okay, so irrespective, but in this scenario it's like this. Okay, for different scenario it will be different. So this is what about the SJF, FCFS and priority scheduling algorithm. And these algorithms you require because in upcoming lab you will be using it, okay, for implementation. So now coming to the point, CPU scheduling or the scheduler, CPU scheduler, there are two different categories of CPU scheduling algorithms. One is the preemptive and the one is the non-preemptive. The one that you have seen till now was the non-preemptive case. Okay, non-preemptive case means you assign a job to CPU. Okay, you assign a job to CPU, or you give the CPU to a particular job. You give the CPU to a particular job. Now the job will not relieve the CPU until unless it completely executed. I repeat, until unless the job is not completely executed, it will not release the CPU voluntarily. Okay, so that kind of algorithm is known as a non-preemptive algorithm. Okay, now we'll try to understand preemptive algorithm. Okay, what is the meaning of preemptive algorithm? Suppose you can see over here, suppose there are 4 jobs, okay, J1, J2, J3 and J4 with burst time 15, 8, 10 and 3 respectively. Okay, and job J1 have arrived at the system at time t equals to 0, and job T2 had arrived at the system or the memory at time yeah, somebody have raised a hand. Okay, just hold on. Yeah, any questions please? Any questions please?
No, sir, I actually accidentally pressed it.
Okay, it's okay, it's okay. Okay, so we are at here. Okay, fine. So these are the jobs with the burst time and the arrival time. So when job J1 have arrived at time t equals to 0, no other job was there. No other job was there. CPU was free, so CPU is immediately given to job J1. Okay, so CPU was immediately given to job J1. So job J1 has initiated the execution from time t equals to 0. At time t equals to 1, it is executing. Time t equals to 2, it is executing. So until unless it don't reach time t equals to 5, job J1 is with CPU or CPU is with job J1. Okay. Now at time t equals to 5, job J2 have arrived with 8 units. So at time t equals to 5, So at time t equals to 5, job J2 have arrived. Okay, till then, job J1 have completed 5 units. Till then, when job J2 have arrived at the system, J1 have already completed 5 units. So the remaining amount of burst time for job J1 is 10 at time t equals to 5. So at time t equals to 5, in the computer memory, job J1 is there and job J2 is there. Job J1 burst time at that time is 10 and job J2 the burst time is 8. Okay, so 10 for J1 and 8 for J2. So whose burst time is minimum? It's J2 obviously, that is 8. So at time t equals to So at time t equals to 5, J2 will begin its execution, and I have placed the remaining burst time of job J1 as 10. You can see in the red color. Okay, so J1 job J2 has started execution at time t equals to 5. Okay, by preempting J1. So the execution, which was supposed to be 15 units of J1, has been interrupted at time t equals to 5 because the algorithm is preemptive. Preemptive means it can be interrupted in between the execution. CPU can be snatched from the current execution. So job J1 was executing initially, okay, at time t equals to 5. Since the burst time of J2 was less, so job J2, the algorithm will snatch CPU from job J1 and will be given to job J2, just because as per the algorithm strategy, just because the burst time of job J2 is less than the burst time of job J1. So like that way we will move ahead. Okay, so job J2 will at time t equals to 10. Okay, at time t equals to 10, in the computer system memory there are three job J1, J2, J3. Okay, with burst time 10, 10 and 10, 3 and 10. Okay, job J2 have already completed. Okay, and then so on. Okay, so it will move ahead. Hold on. Like that way, job J2 have completed. Okay, you can. I'll just flip this slide. Okay, you just need to understand preemptive meaning, so how it will go. Okay, I'll just flip this slide. You can have a look. The color code changes. Okay, this is how one after another the job has been executed. Okay, so that's all for today. If you have any questions, you can please ask. I repeat, if you have any questions, please ask.